J'ai pas de demande. Partager l'écran.
Écoute. De toute façon, si tu vois que ça passe pas, si tu reviens sur Zoom. Ok, let's go for the last talk of Mouad Ramil on parallel Replica algorithm.
Okay, so thanks to the organizer for scheduling my talk after I messed up my schedule. So in this presentation, I will talk about two independent works, but which are both motivated by the same type of question. So in the first work, I'll try to justify an algorithm called parallel replica, which is aimed at sampling the first exit event from a metastable state. And it was done during my PhD at École des Ponts with Tony Lelière and Julien Régnier. And the second work is related to using a method called adaptative metadynamics in order to sample the minimum energy path between two metastable states. It was done at CEO Adam, where I worked with Jean-Bernard Maillet, and it was a joint work with Caroline Boudier, Alexandra Goyava, and Cosmin Marinka. So to quickly motivate this work, so basically, again, the motivation is relying on molecular dynamics methods. So we have many fields which require this set of methods to sample evolution of complex systems. The one which will be interesting for us is in material science through the following dynamics, which was stated multiple times in the previous presentation, which is the Langevin dynamics. So basically, you consider some molecular system composed by a certain number of particles, and you model each one of them by two vectors, position vector in R3 and momentum vector. So this is the Langevin equation satisfied by these two vectors. The first one is just time derivative of position is velocity, and this is the sum. This is the sum of all the forces applied in the system. So you have the force coming from interaction of potential, depending only on the position. And here you have thermostat contribution. So gamma is some positive friction parameter, and inverse of beta is temperature. So as you know, if you want to sample the evolution of this system, namely you're interested in the transition path between one metastable state and another, this often happens at time scale which are much larger than the time scale used for the time iteration, which is of order 1 femtosecond. And typically, you have events that happen at 1 microsecond or even larger. So you have to design other set of methods. And I will briefly mention these two-dimensional examples. So you have one set here, A, another set B, and you want to sample transition path from A to B. So we do 100,000 iterations using standard Euler scheme, and we observe that the system remains stuck in both worlds. You only see oscillation, and this is because the system needs to overcome some energetic gap in order to come to the other state. And you have also another effect, which is entropic effect. Basically, the system needs to find some narrow escape. It happens a lot in large dimension, but also in this case, like the minimum energy path is in this direction, and you see that the escape is orthogonal. So this system will also struggle to find this small escape. So in the first part, I will be interested in how to sample transition event, but without changing the law. So I'll be interested in the exact law up to tuning some parameter. So the algorithm I will introduce here was designed by Arthur Vaughter in Los Alamos National Lab in 1998. It's called parallel replica. And the idea behind this algorithm is to sample the first exit event from some metastable domain by parallelizing in time the sampling. So the first exit event is the time after which I exit the domain and the point from which I will exit the domain. So you start with a configuration where you launched your dynamics, and at some point you notice that it got stuck in some metastable domain for a time long enough. So TOSI is some decorrelation time. So you say, okay, now I can launch my algorithm, and you do it as follows. You start from the last point of the reference trajectory, which is x TOSI, and then you initialize n independent replicas, which follow the same dynamics as x. So basically, you duplicate this reference trajectory by n, and you have n independent replicas. You make them evolve inside the domain. But first, you have to make sure that all these replicas also remain stuck in the domain. So you wait until time TOSI, and you make sure that they stay in the domain. So if one of them exits the domain, then you make it restart to its initial point, x TOSI, until it satisfies this condition. And then the algorithm says that you can sample the first exit event of this reference trajectory by considering only the first exit event among all the replicas. So I star is the index of the first exiting replica among all the n replicas. And you notice that with respect to the time coordinate, you multiply by the number of replicas. So basically, this means that in average, the first exit time among all the replicas happens n times faster than the traditional sampling of this process. So since you sample all the replicas in parallel, what you see in time, in one clock time, is just the time required for the sampling of one replica. So basically, this provides you a speed up of order the number of replicas in one clock time. So what is the idea behind this algorithm is the notion of quasi-stationary distribution, which was introduced in the Tony's talk, which is basically if you consider some dynamics which stays long enough inside some metastable domain, it will reach some kind of local equilibrium, which is called quasi-stationary distribution, and call it QSD in the next. And if you consider a metastable domain, what happens is that you reach the local equilibrium long before you actually exit the domain. So actually, you only need to consider the exit event starting from this QSD. And what is interesting is that, okay, maybe I can quickly say that the QSD can be defined mathematically. So it's a probability measure supported on your metastable set, which is that if you start initially distributed according to the QSD, as long as you do not exit the domain, you remain distributed as such. So this is the meaning behind this conditioning, that if you don't exit the domain, the law doesn't change in time. So the important fact is that if you want to sample the first exit event starting from the QSD, then there is well-known literature saying that the first exit event satisfies some very interesting properties. The first one is that actually you know the law of the first exit time. It is an exponential law. You don't know the parameter, but you can use all the properties related to the exponential law. And this first exit time is independent from the point you will exit the domain. And using these two crucial properties, you can show that if you have n independent replicas all distributed according to the QSD, you can sample the first exit time, the first exit event, by considering only the first exit event among all the replicas. So if you want to properly use this parallel replica algorithm, you need two things. The first one is the existence of a QSD, such that all of this makes sense. And the second thing is that you need the process to converge. If it remains trapped in a long time inside a state, it needs to converge to the QSD. So this is hidden in these two steps of the parallel replica. Basically, I start the algorithm once the process stayed long enough inside the domain. Basically, here, I assume that this process is distributed according to the QSD. And similarly, in the second step, I make sure that the replicas are closely distributed to the QSD. So this existence and convergence question was answered for the overdamped Langevin dynamics. If you consider a smooth bounded metastable domain, so there is a vast literature. You can look, for example, at this article. And in this article by Lebris, Leliev, Luskin, and Perez, they actually formalize parallel replica algorithm using the notion of QSD. So parallel replica is well defined for this kind of dynamics. And if you sum up the results in the literature, basically you have the existence of a unique QSD, and what is interesting is that its density is solution to some eigenvalue problem with zero boundary condition associated to the Fokker-Planck operator. You also have the fact that the law of the process condition in staying inside the domain converge exponentially fast to the QSD. So we want to be able to propagate this kind of result to the process I introduced in the beginning, which is the Langevin process studied a lot in material science. And namely, in our work, we consider more general Langevin process, so a force which does not necessarily write as gradient of a potential, and gamma can be 0 or negative. And in this case, the infinitesimal generator writes as follows. So you have some transport terms, so the velocity, scalar product, and the position. And here you have a bunch of derivatives in velocity. So the main difference with the overdamped case is that this generator is only hypoelliptic, is not elliptic. So all the results regarding smooth regularity at the boundary of solution to the kinetic Fokker-Planck equation do not apply here. So you have to use other set of methods. And the other difference is that we want to consider the case where the force is gradient of a potential. In this case, the metastable domain is Bayesian of attraction of the potential in the position coordinate. So only impose condition on the position, a condition on the position coordinate. You don't have any restriction on the velocity. So the overall domain is unbounded. So if you take upper bound, you have to be careful. Okay. So I said previously that the QSD is some stationary distribution up to conditioning of not exiting the domain. So we have to understand how the Langevin process exits the domain. And this is the main difference with the overdamped case or even some standard Brownian motion. The behavior at the boundary of the process is really different. So namely, you can partition the boundary of the cylindrical domain D into 3 subsets of very different nature. So depending on the sign of the scalar product of the velocity and the outward normal vector. So if this scalar product is positive, then it's the subset from which you will exit the domain. If it is negative, it's the subset from which you will enter the domain. And if it's 0, it's called the set tangential velocities. In the literature, it's also called the singular set or grazing set. And here what happens is that all the solution of the kinetic Foucault-Planck equation, no matter how smooth the domain is or the coefficients, you will experience some loss of regularity, which is due to some loss of information. Basically, when the process reaches close to this set, its velocity is close to 0. So you don't know whether the process will exit or not the domain. And all the solution cannot be smooth around this set of points. So in order to obtain a QSD, we want to, as I've shown before, the density solution to some eigenvalue problem. So we want to build a solution to an eigenvalue problem to the generator. So we start by looking at the semigroup. So we want something which dies at the boundary. So we consider the kill semigroup. So on the event that the first exit time from the domain is larger than t, and you consider this function of time t and initial point x. And first we show that it admits some smooth density. So we study also the regularity and the positivity of this density. But what is important is that it admits some upper bound, some Gaussian upper bound, which is the density of this Gaussian process, which is the Langevin, where you just cancel the force and you divide the diffusion coefficient by the square root of alpha. So some parameter in 0, 1. So what is interesting is that the density of this Gaussian process is explicit. So you can have all sorts of control for this density. And the one which will be interesting for us is that this upper bound is actually in LP d times d. So for any p larger than 1. So this is not obvious because you will integrate x and y on a domain d which is unbounded. So you don't have you have unboundedness on the velocity coordinate. So you have to be careful to not integrate something constant in infinite domain. And using this control, so we can show that this operator is compact. So namely, if you take p equal to 2, so you have this control on the density. And in this case, it's well known that if the kernel is in this space, then you consider a Hilbert-Schmidt integral operator, which is compact. So the important result is that compactness, using a well-known theorem called Krein-Wittmann theorem, tells you that the operator then exhibits some spectral properties. So namely, you can build an eigenvector related to this operator. And this is what we use to provide an eigenvector to the kill semigroup. So we want an eigenvector to the generator. So you know that there is some kind of equivalence between the semigroup and the generator. So this is how we build the solution, the following solution to the eigenvalue problem. So again, we're able to propagate the 3 conditions I stated before. So the existence of a unique QSD with a density and solution to this eigenvalue problem. And again, we have some conversion to the QSD exponentially fast in time. So notice that due to the kinetic nature, again, boundary condition behaves differently. So here you have only on the set of entering velocity. So we have also the results related to the explicit expression of the law of the first exit point starting from the QSD. And we show that it's proportional to the QSD multiplied by this scalar product of the velocity and outer normal vector, which is different from the overdamped case where you have normal derivative at the boundary. And another question we ask ourselves was, we know that if you look at the position of the Langevin process, you rescale in time by the friction gamma, and then you take gamma goes to infinity. It's well known that it converges to the law of the overdamped Langevin process. So the question we ask ourselves, can we have some overdamped limit for the QSD? And namely, we have some limit, and with respect to the position coordinate, we obtain what we would expect, which is the QSD of the overdamped Langevin process on the position domain. And if we consider the whole weak convergence, we show that it's proportional to the overdamped QSD and some Gaussian in velocity. So what is interesting here is that if you take the overdamped limit, the position and the velocity of the Langevin process start behaving independently, which is not clear for general forces. So So if you want to look into more details regarding these results, I refer you to this research letter by with Tony and Julien. And now I will move on to the second part related to metadynamics. So in this case, I come again to the previous 2D example of the Mueller potential. And we want to sample some transition path between A and B. So starting from A, we want to sample this minimum energy path going from A to B, and this minimum energy path from B to A. So metadynamics, so I will briefly explain what it is, but the main required tool to be able to use this method is to define a proper collective variable. So it's a function which go from the phase space to a lower dimensional space, and will take different values in the metastable state and transition state. And the idea of metadynamics is that throughout your trajectory, you penalize the spot you visited. So every time you visit a spot, you add some Gaussian to the potential, such that you have less chance to explore again this place. And you keep doing that. It's like adding sand of bags, a bag of sand every time you visit a place until you fill the well, and you start doing it. And at some point, you end up with filling all the wells, and you sample uniformly throughout the path. So if you have a good collective variable, which tells you this is the first state, this is the end state, then you can sample uniformly throughout the path by avoiding the metastability. So we use an autoencoder to train to obtain the collective variable. So what we do then, so we have some data we sampled on A and B, and we train an autoencoder. So to obtain the collective variable. So we obtain a collective variable which gives us pretty much some constant value here, another constant value here, and it brutally increases in between. So the issue is that the metadynamics does not manage to find an exit, because pretty much the collective variable here and here is constant. So sometimes you initially train and you have some poor initial condition of the collective variable. So the second naive way to do it was just to draw a line between the two metastable states and to take the linear projection from A to B. And if you do that, actually, from B to A is pretty much you obtain the trajectory you expect. But here you see that it's basically orthogonal to the minimum energy path. So what we want to do is to train the autoencoder like successively every 1,000 iterations. We retrain the autoencoder. And doing that, we're able to follow the minimum energy path locally. But again, this nominal escape is not found because we do not provide enough information. So the system will just keep growing here, and we'll never see this escape. So we try to, in the training of the autoencoder, we try to provide the information that we want to sample a path from A to B. So we add this condition that the loss should contain, I don't see it. So the loss should contain to properly reconstruct the center of mass of A and center of mass of B. And we can actually plot the path suggested by the autoencoder. So if you project the center of mass of A and B into using the encoder, and then you discretize, you provide a linear interpolation. Then if you decode properly, so you project the center of mass of A and B using the encoder. Then you do some linear interpolation in the latent space, so in the one-dimensional space. Then you decode all of these points to obtain points in the phase space. So actually, if you look at this succession of points, it will give you the path suggested by the autoencoder. So we do it and we obtain some nice results. So we wanted to see if it will be, if we still obtain a nice result if we change a little bit the Mueller potential. And in this case, we obtain a path from here to here. So actually, it satisfies all the conditions we give it. It's a path from A to B. It follows locally the minimum energy path. The only issue is that here you have two possible paths. You have this one, and you have this one. So we want actually to add in the condition that it should choose the path which minimizes the energy throughout the path, throughout the training. So we add this last condition, and I will finish here. So basically, we want throughout the training, we want to sample a path So here you have a first contribution, which is 2 successive points in the trajectory suggested by the autoencoder should be minimal. So we don't want like big jumps in the phase space. And the second one is that throughout the discretization, you want that the potential remains minimum. So you don't want big jumps to saddle points or above saddle points throughout the trajectory. So doing that, we're able to extend this result even for this more complicated Mueller potential. And what is interesting is that, like, throughout the training, it's able to try to anticipate the future trajectory. And here, even before the process manages to escape this state, it also has something which is very close to the minimum energy path. So this is at 25,000 iteration, and after it stays a long time here, it manages to converge to this minimum energy path. But so I think I will stop here. Thank you very much for. Okay. Yeah. So what is interesting is that, as I've just said, you're able to anticipate the transition path. So the question which remains is that if you have multiple potential paths, how the autoencoder will be able to distinguish between two paths. So will it oscillate or will it choose a particular path? And the second question, which is, I think, ongoing works and future works, is what happens in high dimension. Can you expect? So in all this work, we use basically autoencoders. So neural networks which expect to be pretty efficient in high dimension. So all of this work should be scalable to higher dimension. So yeah. So I thank you for your attention.